previous video, we did a setup stage where we trained a multilayer perceptron for comparison purposes, and in this video we are going to swap out the multilayer perceptron with a convolutional network that we are also now going to train on MNIST. So we are going to use the exact same notebook that we ended with in the previous video. So we are going to rename this, and we are now going to implement the CNN. So we are swapping the multilayer perceptron with a CNN to classify the same images in the MNIST dataset. So we are just going to rename this notebook as well so that it doesn't become confusing. So this is now the CNN notebook. And yeah, I'm doing this to show you that this is exactly the same notebook, except of course that we are now using a CNN. So let's scroll down to the relevant part here, the PyTorch multilayer perceptron, and swap that out by the CNN, the PyTorch CNN. So I will just paste that in here. And let's now briefly discuss how it looks like. So the structure is essentially that we have CNN layers and then we have fully connected layers. These are the classification layers. We can really think of the CNN layers as feature extraction layers that are then followed by a type of multilayer perceptron structure here. So if we look more closely at the CNN layers, we have different convolutional operations. We have a convolutional layer, we have a batch norm layer, a ReLU activation function, and a max pooling layer. So I would say this is one block here. We can consider this as a block where we have convolution, batch norm, nonlinear activation, and pooling. And then we repeat this block here, and then we repeat this block one more time here. So it's essentially like a hierarchical structure here where we are extracting features from the original images into these several blocks where we are creating new feature maps in each block. And notice here, while the feature maps will become smaller over time, we are increasing the number of channels. So originally images in MNIST are grayscale images, so they don't have a color channel, so they only have one input channel. And here we are increasing it to 3 output channels. So we go from 1 input to 3 output channels here. Then next we go from the 3 input channels, so the 3 comes from here. So we are ending with 3 output channels. Then we take the 3 input channels in the next block and produce 16 output channels. And then we take the 16 channels and produce 32 channels and so forth. So we have now 32 channels. And at this point, the images are 1 by 1 images. You can't see that here, but if you would do the math, you could calculate that these are 1 by 1 images. So we have now 32 features at this point, which we then feed to the first fully connected layer here. So we have 32 features. And we squeeze that to 20 features. And then we take the 20 features and convert that to 10 classes. So I should say everything, or the numbers here, are quite arbitrary, except of course for the structure where we go from a small number of channels to a large number of channels. But everything I've chosen here is pretty much like based on, let's say, some domain knowledge, I would say, but also mostly on gut feeling, what works well, and also by trying out different things and see if they work well. In practice, people rarely design their own CNNs. In practice, what we usually do is we use a pre-established CNN structure or architecture that is already available. Because researchers spend a lot of time developing good architectures, and it's usually a good idea to reuse existing architectures that are proven to work well instead of, let's say, designing your own architecture. But I just wanted to show you how it looks like, so how we can make our own architecture here. So, and then once we have our layers here implemented, we have the forward method. In the forward method here, we call, of course, our CNN layers first. So here we extract the features. Then we flatten these features because they are two-dimensional features. This is analogous to the MLP in the previous video. And then we feed the flattened vectors, so essentially feature vectors, to our fully connected layers. You can really think of this as a multi-layer perceptron here. So this is really a multi-layer perceptron part. And I also wanted to say that I left this in on purpose here, this print statement. So this is a very quick and easy, quick and dirty trick to find out what the number of features are that should go into the linear layer. Because when you try to implement your own neural networks, you can calculate how big the feature maps are that are produced by the CNN layers here. So you can do math based on all these operations, based on the kernel size, the padding, and the stride, and find that out. But a really quick and easy way to do that is also just to have this print x shape here, where you will then see what the output is, what shape x has, and then you know what the dimension here should be. So if you have the shape and you calculate the number of height pixels, the width pixels, and the number of channels, then you know what the number of input for the linear layer should be, which is a simple and easy trick to, let's say, find the right number here. Okay, so in the rest down there is all the same that we used before. So let's run this and see how the results look like. Oops, I made a mistake. Of course, our network is now called CNN, so I should also change this, of course. And we don't need the num features anymore. Okay, so the training has finished. It took a bit longer, but as we can see, the results are pretty good. So we have also the validation loss going down over time, and of course also a good validation accuracy here. So that looks all great to me. And the test accuracy is also pretty high, 98.5%. It's not that much higher than the performance, let's say, of the multilayer perceptron, but that's because it was already very high to begin with, because that's a relatively simple data set. In a real-world project, you will find that MLPs, multilayer perceptrons, would perform very poorly on images. And also you should note that, yeah, of course, when we have larger images with larger resolutions, the number of pixels will be so large that you won't be able to process them even with a multilayer perceptron, because the number of features in the first hidden layer will be just too large, and then you will run out of memory when you try the computation. But again, so this was an example of how we can use a convolutional network. And in the next couple of videos, we are going to explore a different data set and different architectures. So in this video, we swapped out a multilayer perceptron with a convolutional neural network. Congratulations to training a first convolutional neural network. In the next video, we will take it a step further and introduce a new, more challenging dataset, Cypher 10.